Hello and welcome to our lecture. Today we're going to cover a topic that for some may come off initially as a little bit challenging. There will be a homework that is relatively simple around this concept, but it may take a little bit of time for those for which this is a difficult concept to kind of think it through and work it out. But if this clicks for you really quickly and the homework seems easy, don't worry about it. It is intended not to be difficult. It's just intended to make sure that you work through at least one problem using today's concept, which is called recursion. Recursion is a relatively simple concept where a method, as part of its algorithm, calls itself. I'm going to start this off with a very simple example. Calculating, taking one number to the power of another number. Now it's gonna look from a programmatic standpoint, very old school, very CIT 130. But the idea is to focus on the concept of recursion rather than sort of the aspects of the Java language here. So this is going to be relatively simple. So I'm going to start with a static method. We're not going to create any objects from this power class. It's going to be just static. There's going to be a method. It's going to return an integer, and we're going to call it exp for exponent. And we're going to have the base and the power it's taken to. So it would be, in essence, taking b to the p power is what this is going to do. Now this code is going to be incredibly short and simple, which will be one of the themes that you will notice in recursive algorithms. So if p is greater than 0, what we want to do is return the base multiplied by a call to exponent with the same base to the p minus 1 power. I'll explain why we're doing this in a couple of minutes, but just for now, let's just look at what we're doing. And otherwise, we will return the number 1. One of the things that you'll notice about a lot of recursive algorithms is they work backwards, where we have the p minus 1 here, and they're clearly, in order to prevent an infinite recursion where it never ends, we do need to have what we call a terminal or end case, such as this here. So what is going on here? Let's add a main to this so we can see how it works, and I will walk through the solution or the running of the program for you so that you can see it in action and hopefully get the idea. We will be doing a more complicated example to see another way of or to see another one, and then you'll get a chance to work through one on your own. But let's just set a base and a power. So we'll be taking 2 to the 8th power, which, is what? 2, 4, 8, 16, 32, 64, 128, 256. We'll do a now system.out. .println exp base power. So we're going to take base to the power. So down here at the bottom, as a note, I'm going to kind of show you how this works. So just think about the base running of the method. We're sending base and power to primitive type variables, so we're just sending the values 2 and 8 in. So when we check locally, they'll be called B and P instead of base and power. So we're checking, is the power greater than 0? Clearly 8 is greater than 0. So what the answer is, or what will be returned, is 2 times the exponent of 2 to the p minus 1, which is 7. Now, one of the ways I'd like you to think about this, if I told you we had 5 times math.abs negative 5, you would understand that is 5 times 5, because the absolute value of negative 5 is 5, and that we would ultimately have 25 as the answer. The recursive algorithm isn't going to work too differently than that, because what we're returning is 2 times some method that happens to be called exponent, or exp, 2 to the 7. So what does that equal? That equals 2 times, well, when we call exponent, 7 is greater than 0, so that's going to return base times exponent of 2, p minus 1 is 6. No biggie. We now have 2 times 2 times, well, what's that? We send 2 and 6 to exp. 6 is greater than 0, so we return 2 times exp of 2, comma, p minus 1 is 5. 1, 2, 3, 1, 2, 3. Hopefully you're starting to see a pattern. I'm going to use less parentheses because they get hard to keep track of after a while. But ultimately, we now have 2 times 2 times 2 times whatever exp 5 is. 5 is greater than 0, so that's 2 times exp b, which is 2, sorry, p minus 1 is 4. So what does that equal? 2 times 2 times 2 times 2 times exp 2, 4. 4 is greater than 0, so we get 2 times exp of the base, power minus 1 is 3, equals 2 times 2 times 2 times 2 times 2 times the exponent, or exp, of 2 to the 2. Let me go to the next line. That is 2 times 2 times 2 times 2 times 2. 1, 2, 3, 4, 5. 4, 5. Times exponent of 2, 2. 2, which is now p, is greater than 0, so we return 2 times exp of the base, p minus 1 is 1. That's going to give us 2 times 2 times 2 times 2, 1, 2, 3, 4, times 2 times 2 times exp of 2 comma 0. And let me just check my work here. 2 times that, so then we have 2 2's, then we have 3 2's, then we have 4, then we have 5. Oh, I missed one on this one. So this one should have had 6 2's. 3, 6, 7 2's. 2 times 2, and this one has 8 2's. So what does that equal? That's the 8 2's times 2 times 2 times 2 times 2 times 2 times 2, 2, 4, 6, 8. And the exponent 2 comma 0, well, p is 0 now, so it's not greater than 0, so instead we return 1, which is the identity, and anything taken to the 0 power is 1 anyway, so this makes it work out. So what is 2 times 2 times 2 times 2 times 2 times? That's going to be 256 because it's multiplied by itself the 8 times. So this is relatively simple. If you just run it through without overthinking it, it comes out naturally. As long as our power stays above 0, we're going to take the base and multiply it by the same base to 1 less power. And if you think about how powers work, it's exactly right. So 2 to the 7 is 128. So 2 times 2 to the 7 is 256. 2 times 2 times 2 to the 6th, 2 to the 6th is 64. 2 times 2 is 4 times 64 is 256, and so on. Conceptually, it's no different than what we did here. It just takes longer to get from the beginning to the end. And the way that we kind of know a problem is a good candidate for recursion is when you have a repeatable step that truncates or terminates at a very specific time or a very specific condition. So hopefully that kind of makes sense. A better commented version has already been uploaded. So theoretically what I would do is I would save this. I'm going to save it locally because the real one's already on my drive. So we'll have power.java, save, and we'll zip out here. And we will have not catch. This is power.java. And while that's taking a moment to compile, just really to look at it, we're just simply saying that we can take the base and multiply it times the same base to one less power. Because really, a power is just the same base multiplied against itself, power number of times. So every time you drop the power by one, you can just multiply by the base again, and you have um, the identical operation. So a very similar example is in the textbook that shows how to do factorials. Both power and factorials I teach in the CIT 130 class when we're learning deterministic loops. Oh, I did some mistakes. Oh, I don't know why I made those. I put a axis modifier on those. Sometimes when I'm chatting, uh, the mouth works faster than the head. Those can just be plain integers. They don't need an axis modifier on them. They're just local variables to the main method. So ultimately, we're doing similar to what we would do with the for loop, but it kind of it's a very concise way to work. The amount of code here is incredibly small. The actual code for the recursive method is a header and 2 lines. We're going to do a slightly more complex example here in just a couple of minutes once I show that this one works, and we'll get a chance to see something a little bit different and a little more complex. So hopefully that, even though it'll be a little bit harder to follow, hopefully it'll help drive home the concepts a little better. So as we expected, the answer comes out correctly. So now I want to do a second problem. It's going to be a public class US volume converter. Now, one of the things that, whoops, gosh darn it, that you should have seen by this time in your Java development, TechNet, or Tech Network, there we go. Let's go to the Java page is the math class for Java SE. So if you go in to java.lang, that's the API library that we get without importing in all Java applications. If we look at this math class, what you'll find is there are some static constants, e and pi, which are commonly used in mathematics, and a number of static methods that correspond to various mathematical operations. So, like I said, you'll see e and pi are both constants, and then there's a bunch of static methods and nothing else. No constructors, because we don't make maths. We just use mathematical operations. This is not an uncommon way to create some sort of function library. So I'm going to do something extremely similar here for the confusing US volume uh, conversion world. So I'm going to make a public static final int, and I'm going to call it teaspoon. That is going to have a value of 0. Now, it'll become clear in a minute or two why I'm doing these as consecutive integers rather than some, we'll call it conversion factor. This is going to correspond to something, and it's really going to play into our ability to make a very, very clean recursive algorithm. So we have teaspoons, we have tablespoons. That leads us to ounces. Oops, teaspoon, tablespoon, ounces is 2. Public static final int cups is 3. Public static final int pints is 4. Public static final int quarts is 5. And public static final int gallons equals 6. Now I'm going to add one last thing. Public static final conversions. Double array conversions equals, and we'll make this a pre-filled, and this is 1 teaspoon makes a teaspoon, 3 teaspoons makes a tablespoon, 2 tablespoons makes an ounce, 8 ounces makes a cup, 2 cups makes a pint, 2 pints makes a quart, and 4 quarts makes a gallon. We should have 6 conversion factors: 1, 2, 3, 4, 5, and 6. You'll notice, even though it will work if you just put 1, 3, 2, 8, 2, 2, 4 without the point zeros on them, because of possible issues with integer division, I always put the point .0 on integer versions of doubles if I want them to specifically be a floating point number, which is what I want. So I'm going to make a single method, public static int convert, which is going to take in a start value, how much of whatever it is we're converting do we have, convert from the unit, and I have to give these types, int convert from, int convert to. So with those three pieces of information, we have everything we need to know to be able to do the conversion. So, a couple things I want to talk about before I actually write the full code. So you should notice that with my 7 different US volume units, I have put them in order from the smallest unit to the biggest unit in terms of how much volume that unit holds. So a teaspoon's very small, a gallon is quite large. So that by putting them in order and then assigning them a numeric value, I have now made these units objectively comparable for bigger and smaller. Despite the good naming convention on these constants, teaspoon, tablespoon, ounces, cups, there's no way for the computer to be able to quantitatively compare the variable named quarts to the variable named ounces based on how much volume they hold or anything intrinsic about the name of that variable. It could care less, but when we assign them unique incremental values, we have now made it super obvious that a teaspoon is smaller than a pint, and so on. The other thing that gains us is the conversion factor to go to or from this to the next largest or smaller value is held inside the array at an index that corresponds with its integer value. So teaspoons can't get smaller, so theoretically converting teaspoons to teaspoons is a factor of 1. And that is important to our algorithm. So this follows very much stuff we've looked at all semester when we were doing things like colors and orientations in our Java FX applications. We were using those sort of color dot blue, which were assigning some integer value to a variable to give it some kind of unique value to use that's easier to remember than some random integer that, numbers aren't intrinsically blue, so trying to figure out which number goes with blue versus magenta versus chartreuse can be a pain. So this is an incredibly common idea in Java programming. So, just like we did in the powers example a few minutes ago, we need some cases. In this one, there will actually be 3 cases, one for converting from a bigger unit to a smaller unit, one for moving from a smaller unit to a bigger unit, and one for when the conversion ends, which works identically regardless of which direction we go. So let's start with if convert from is greater than convert to. So here's where that objective ranking system of 0 to 6 works. If I'm converting from gallons to teaspoons, gallons is going to be larger than teaspoons. When we go from larger to smaller, we're going to be doing some multiplication because 1 gallon is going to be a large number of teaspoons. So the start value is going to get much larger going to the smaller unit. So if that happens, what we do is we take our conversions array, we look at the convert from, so we're converting, let's say, like I said, from like gallons to teaspoons. We take that for that first conversion factor that converts gallons to quarts or quarts to gallons, and we multiply that times convert start value, convert from -1, comma, convert to. So just like in the power example, what we're doing here is let's say, for example, we have 10 gallons and we want to go to teaspoons the whole way down. What we've done is we've said we have a conversion factor of 4 to 1 between gallons and quarts. So if I multiply my value by 4, I will now know how many quarts I have from the original. But I know quarts isn't what I want, so let's go further down the line. We still have the same start value, and that's going to come to play at the very end in the terminal case. Oops, I don't know why. Time. So the start. Whoops. So in this case, that start value is 10. So now what we're going to do is we had gallons, which was 6. Now we want to go to from -1, which gives us 5, which is quarts, if you see above. And the end is still teaspoons, which is 0. Now, ultimately, when you actually, you can think of 5 is US volume converter dot quarts, and 0 is US volume converter dot teaspoon. So think of it that way, or just as the numbers, whichever makes this wind up being easier for you. Again, just like the other one, if you don't overthink it and just look at it and say, okay, what happens when I call convert with 10, 5, and 0? Convert from is definitely bigger than convert to, so I'm going to pull the next number, which is 2.0, and multiply that times convert with the same base, 1 less on the from, and the same endpoint. 4 being pints, 0 being teaspoons, and if you just follow the logic, 2.0, when I do a convert with 10, 4, and 0, 4 is greater than 0, so that means I go grab the next element, which is now sub 5, index 5, times convert 10, 3, 0. Again, I hope you're noticing the trend. 4.0 times 2.0 times 2.0 times um, when we call convert 1030, 3 is greater than 0, so we get the next conversion factor, which is now 8.0 times convert, same base, 1 less on the from, same 2, 4.0 times 2.0 times 2.0 times 8.0 times convert, oops, that was supposed to be 2 because it was minus 1, the convert from minus 1. So we go to the next conversion factor at index of 2. That's a 2.0. We multiply that times convert, same base, 1 less on the from, same on the 2, 4.0 times 2.0 times 2.0 times 8.0 times 2.0 times convert 1, 10, 1, 0. 1 is greater than 0. So we pull the conversion factor at 1 and we multiply that times a call to convert with the same base, 1 less on the from and the same 2. 4.0 times 2.0 times 2.0 times 8.0 times 2.0 times 3.0 times the answer to convert 0, 0. Well, 0 is not greater than 0, so we need another case. I'm going to throw the else case in here. There will be a case in between. I will show you that momentarily. But the else case, you know, that may at some point or another, you know, make you think a little bit. Is it 1? Is it, do I want that unity factor? Do I want whatever? But when you look at this expansion down here, one of the things you'll notice is that 10 starting value is still not in the equation. Again, we're working backwards. So when we work backwards, the starting number is what we're going to want here. So we get that by doing return start value. And this right here was a return. So let's think about the second case. Convert from is less than convert to. And you may immediately be thinking, well, what if they're equal? That's what the else case is for. When they're equal, I don't need to do a conversion. The start value is the end value. No multiplication needed. I return just the start value. Otherwise, if I have to do the recursive calls, the last thing I multiply by is the original number. And even though it's technical, this 10, its conversion factor down to quarts is way over here. Multiplication is commutative, so we can put them in whatever order, and this makes clear sense because we do the recursive piece and then multiply it by the real answer. So in this case, what are we going to return? Well, one of the things that hopefully you've learned along the life of your life in I lost my train of thought, in mathematics, is that division is the same thing as multiplying times 1 over the what we're dividing by, meaning 1/3 is the same thing. 1 times 1/3 is the same thing as 1 divided by 3, or 9 times 1/3, which is 3, is the same thing as dividing 9 by 3. Hopefully that made sense. So what we're going to do is we are going to multiply by 1 over conversions convert, whoops, I don't want the caps, convert to, that's going to multiply times convert, and this is where we have to think. Again, we're holding on to the start value till the end. So we know that in all the recursions, that has to be sort of held on to till the last operation. So as this goes through this recursively, it just keeps passing it to the next iteration. So we're going to do, convert from. We're not going to touch this case because we're sort of walking the opposite direction. So what we're going to want to do is the convert to minus 1. We're walking what we're converting to down instead of walking the convert from down, because we're going the opposite direction, if that makes any sense. Again, multiplication is commutative, so whatever order the multiplications go in isn't the key. The key is making sure that we get the right answer. Now, when I talk about this, it may seem like I'm coming up with really crazy stuff off the top of my head. Now, this is a bit more complex than the power, but it's still 100% the exact same idea. I'm starting with some value and walking through the steps one by one by one of the calculation. Any algorithm that has that sort of, I can stepwise my way to the final answer doing the same operation over and over again, recursion should come into your mind, and you may have to sit down with it for a little bit and kind of play with the answers, or go with your gut, and if you get the wrong answer, walk it through like I did. Walk it through, and if it's right, you'll see it work, and if it's wrong, as you walk it through, hopefully you'll get to where you need to be. If, again, when I was talking like the what do I return in the else clause, if let's just say you went with your gut instinct and said, you know what, I think it should be 1, you would quickly realize by playing with it, no matter what your start value was, if you go from one unit to another unit, you're always going to get the same answer, no matter how many of the starting unit we said we had. And then you'd probably realize, oh, I don't want 1, I want the start value. So let's go ahead and save this one. And I want, it's going to be in the same place. US volume converter.java, save. Let's just make sure I didn't make any stupid mistakes like I did in the first one. Java C, US volume converter.java, and I made some mistakes. Let's see. These were all ints. Those were all doubles. I'm going to have a double start value. I'm going to convert from something to something. The conversions, sub, convert from, and then we'll convert start value from -1, convert to. What line was that on? So I'm a little perplexed. It's saying from double to int. I'm a little confused. Let me look at it one more time. Multiply. Start value came in as a double. It's leaving as a double. Conversion sub convert from. It's got that's coming in as a double. It's going out as a double. Convert from -1 to convert to. Oh, can't believe there's my mistake. Very simple, very simple. Let's see if that cleared up everything or if I still got. Nope, that was it. Sorry about that. Again, I like to fly without a net so that when I make a mistake, you can watch me work through it and get some insight into the kinds of things you need to be checking for when your stuff doesn't work. Oh, again, talking before I act, this was meant to just be sort of a library like the math is. I need one additional program which will hold my main. I'm going to just call that public class test converter. And that is going to have a public static void main string args. That's going to be system.out.println. And when I call this, hopefully you'll see sort of the way I thought it through. It's going to be US volume converter dot convert 10 US volume converter dot gallons to US volume converter dot teaspoon. I think it was teaspoon, not teaspoons. That's correct. And so we're taking 10 gallons, converting it to teaspoons. That's the way this is supposed to read. We're calling static method, static constant. That's why we refer to the class. They're static methods, not object members. This is going to be called testconverter.java. Let's go out here, Java C, testconverter.java, Java test converter, and that is indeed the right answer. So essentially what it winds up doing, the way to look at this is we're saying we have some amount of gallons or quarts or pints or cups or whatever, and we want to go to teaspoons or tablespoons or whatever. And so we know that we can do it in steps. So to go from gallons to quarts, I have to multiply by 4. To go from quarts to pints, I multiply by 2. To go from pints to cups, I multiply by 2. To go from cups to ounces, I multiply by 8. To go from ounces to tablespoons, I multiply by 2, and so on. And it'll work no matter where I start and where I end. And if I'm going the other way, if I'm going, say, from teaspoons um, uh, to pints, I know that teaspoons uh, to teaspoons is 1, teaspoons to tablespoons is 3, tablespoons to ounces is 2, ounces to cups is 8, cups to pints is 2, and then when I've reached the end, when what I'm converting from and to are the same thing, that's when I throw back the start value, and we wind up with what I showed you down here. Play with it, download it from the site, play with making your own test converters. It really is just these two lines of code, and no matter what you put in for these two things, it will convert properly. Whether this is bigger than this, or this is smaller than this, or whether they're the same, you'll find that it works either way. And just put in different numbers, and use a conversion calculator on the internet or on your phone to check the work and the answers, and think through how it does it. Draw this out on a piece of paper as it converts either direction, and try to wrap your brain around it, and I think it will click. So once you've got it, there is a new homework posted on the site. If this clicks, it will be very simple. If it doesn't, you'll have to play with it a little bit till you get there. I just want you guys to really think through one recursive algorithm on your own, without too much help from me. Now, one thing I talked about briefly in class on Wednesday but didn't get to, I'm going to show on this power one other thing. Some folks may have seen this in their CIT 130 class. There's a special thing called a trinary operator in Java. It's also in a lot of other languages like C++ and C, where what we can do is we can do a single operation where we do p greater than 0, and I usually like to put that in parentheses. We question that. If it's true, b times exponent b comma p minus 1, and otherwise 1. It's called a trinary operator, and I'll put this in parentheses too, just so it's crystal clear. We're basically saying evaluate this. If it's true, the answer's here. If it's false, the answer's here. It's a shortcut. If that doesn't make sense, use that up there. But for those who can who see that and go, oh, that makes sense, evaluate this. The answer for true, the answer for false. Trinary operator. It's kind of cool to learn. Let me go back and Java C power.java. We're not going to see any different answer. It's still 256. So that's just a little bonus there, a little extra piece to help you see how this all, just to kind of learn a new thing. If you've never seen the trinary operator, it is kind of neat. It's very optional. You can do everything you want here. So if that doesn't make sense, the recursion's the important part here. Look at the two examples. They're both uploaded to the course shell. Um, work on the homework. If you have questions, let me know. And we'll talk to you all again next week. Take care and have a good one.